Dear viewers, welcome to our TCE Made Easy series of civil engineering concepts. So in this example, let us see how to analyze a continuous beam by using moment distribution method. We'll see the steps involved. So this is a two-span continuous beam. So span AB is subjected to 2-point loads of 10 kilonewton and 15 kilonewton at 1 meter and 1.5 meters from the left, and a UDL of 15 kilonewton per meter over the span BC. Say EA is constant. Step 1, first step is stiffness and relative stiffness. So for that, write the span. So we have two spans, AB and BC. So write AB, BC. Then mark the length, say our span. Say span AB is say 2.5, 3 meters. Span BC is 3 meters. Then write the moment of inertia. Since EA is constant, moment of inertia will be II only. In case we have varying moment of inertia, this may be 2I or I, or this will be 2I or I, or this will be I, or this will be 1.5 likewise. In that case, you need to mention the I values. Here EA is constant, therefore I is same. Then we need to find the stiffness. So with regard to stiffness, say stiffness is defined as the ratio of moment of inertia to span. Say for example, if you take span AB, A is fixed and B is continuous support. A is fixed and B is continuous support. Therefore, the stiffness will be I divided by L. So moment of inertia I is I, then the length is 3, therefore I divided by 3 for span AB. In case of span BC, span support B is continuous where C is freely supported. So whenever you have a freely supported end or a hinged end or a roller support here at the end, then 3/4 of the stiffness will be there. When these supports, say with regard to AB, A is fixed and B is continuous. So you will have full stiffness, 100% stiffness. And when you have any one freely supported end like this, then we will have only 75% of the stiffness. So 3/4 into I by L. So 3/4 into I divided by 3. So this is I by 3 and this will be I by 4. So this is I by 3, and if you simplify this, it will be I by 4. Then in order to make the calculations easier, we will go for relative stiffness. That is, we will convert this into a mere number. So we will make this as a mere number so that we can use this for further calculations of distribution factor as well in the moment distribution table. So let me multiply, either I can multiply both these values by 3 divided by I. Say if I multiply by 3 by I, 3 will get be 1 and IA will get, therefore this will be 1. And if we multiply by 3 by I, then this 3 already cancels, so 3/4, so I will get cancelled, so 0.75. But I am multiplying by 4 by I, so that is optional. Either I can go by, say this is I by 3 and this is I by 4. So either I can commonly multiply by 3 by I or 4 by I. So if I multiply by 4 by I, then IA will get cancelled, 4 by 3 will be 1.33. and 3 will get cancelled, already I have 4, so we'll be having 1. So this is called relative stiffness. With respect to this, what is the stiffness? Similarly, with respect to this, what is the stiffness? So that is called relative stiffness. A best example will be relative speed. Say if a car travels by 30 km per hour and another car travels by 20 km per hour, the relative speed will be 10 km per hour for the first car. So likewise, this is a relative stiffness. Then distribution factor. So distribution factor, we call this as DF. So DFAB equal to 0 since A is fixed. Distribution factor at fixed support is always 0. And DFBA, so we want to find DFBA. So distribution factor is defined as the ratio of stiffness of the member considered to the sum of stiffnesses of members meeting at that joint. That is the definition for distribution factor. So if I want to find distribution factor for BA, it will be stiffness of this member, say KBA. Therefore, this is in the numerator, KBA divided by sum of stiffnesses of members meeting at the joint. So at this joint, there is BA to the left side and BC to the right side. Therefore, stiffness of BA and stiffness of BC will come in the denominator. So KBA plus KBC. And KBA, these values are available here. So KBA means 1.33. So 1.33 divided by KBA plus KBC. So KBA is 1.33, this is 1. Therefore 0.57 will be the distribution factor for BA. Then distribution factor BC will be KBC, that is sum of stiffness of BC divided by sum of stiffness of the member BC divided by sum of stiffness of members meeting at the joint B. Therefore, this will be KBC by KBA plus KBC. So KBC will be 1 and divided by KBA 1.33 plus 1. Therefore, this will be 0.43. And it should be remembered that any support other than fixed support, at any support other than fixed support, sum of distribution factor will be 1. So if you add these two, 0.57 plus 0.43, you will be getting 1. Then DFCB equal to 1. So distribution factor for CB, since C is a freely supported end, the distribution factor is 1 for freely supported ends. Then we need to do the moment distribution. So moment distribution, let us see how to do. So first write the joints. So we have 3 joints, namely A, B and C. Then write the member. At joint A I have only one member AB. Whereas at joint B, to the left side I have member BA and right side I have member BC. At joint C we have only one member CB. So this write the member. And we should write in such a way that, let's say B is a common support. So this side you write the left side member and this side you write the right side member. A is we have only one member, then no problem, you can write below this. Similarly C we have only one member, so write below this. Then write the relative stiffness. So relative stiffness of AB and BA is 1.33, 1.33. Relative stiffness of BC and CB is 1. So write. Then write the distribution factor. The distribution factor we have all calculated in the previous step. So 0 for A, 0.57 for BA, 0.43 for BC and 1 for CB. Now we are going to start the distribution. So first write the fixed end moment. First write the fixed end moment. So fixed end moment need to be found before coming to this step. So fixed end moment. So fixed end moment will be, say we have 2 point loads. We have 2 point loads. So we know how to find the fixed end moments. So fixed end moment will be it has to be split into 2. So minus W1 A1 B1 squared by L squared minus W2 A2 B2 squared by L squared. For M of BA will be plus W A1 squared B1 by L1 plus W2 A2 squared B2 by L2. So using that you can find the fixed moment. And fixed moment for UDL will be minus WL squared by 12 on the left side plus WL squared 12 on the right side. So the fixed moments should be calculated. Say those values are this: minus 10.07, 7.85, minus 11.25 and 11.25. So this is M of AB, M of BA, M of BC, M of CB. So before starting the actual moment distribution, we should see whether there is any freely supported end. So in this problem, A is fixed, B is continuous and C is freely supported. So at the freely supported end, if it is roller or if it is hinged, then the final moment at this end should be equal to 0. So that we will be doing first initially. So identify any free support or freely supported end is there. So here C is freely supported, wherein we have a moment of 11.25. So first balance that moment. So balance this moment by applying minus 11.25. In case if we get minus 11.25 here, then it should balance by plus 11.25 here. So this is balance, next step. Then carry over. So whenever you apply a moment at one end, half the moment will be carried over to the far end. So from CB to BC, BC to CB. So for BC, this is the far end and this is the near end. For CB, this is the near end, this is the far end. So half the amount will be carried over to the far end. So minus 11.25 divided by 2 will be minus 5.63. And here we will not have any values because there is no value here. Only we have value here minus 11.25, here 0, therefore 0. So half the amount will be carried over. Now we need to finalize the fixed end moment. We need to finalize by adding from here. So minus 10.07 here, here 7.85 here, and then minus 11.25 minus 5.6 will be minus 16.88. Then if I add this 0. So hereafter we should not touch this end because this is a freely supported end. So we have made the moment as 0. So hereafter there should not be any carry over or distribution at this end. Now this we call as a finalized fixed end moment. This is the initial fixed end moment. Then by applying this balance and carryover, we need to finalize the fixed moment. So this will be minus 10.07, this will be 7.85, this will be minus 16.8, and this will be 0. Now we are going to do what is called as distributed end moment. So for distributed end moment, we need to see every joint. So consider joint A. We have minus 10.07. So to balance this or to make it 0, we need to apply plus 10.07. So therefore it will be, the distributed end moment will be the moment which needs to be balanced multiplied by the distribution factor. And since distribution factor is 0, we need to multiply minus 10.07 by 0, therefore 0. Then here, 7.85 minus 16.88 will be minus 9.03. So to balance this, plus 9.03 need to be applied. So you write this using pencil here. This 9.03 need to be distributed to the ends B and BC with regard to the distribution factor. So this 9.03 multiplied by 0.57 is 5.15. 9.03 multiplied by this factor 0.43 is this. So this is one cycle. Fixed end moment or distributed moment, carryover moment will be distributed will be one pair. So this is one pair. The next step will be carryover moment. So from AB to BA there will be carryover. Similarly from BA to AB there will be carryover. So here 0, therefore 0 will be carried over here. Here 5.15, half the moment will be carried over, so 2.58. Then here 3.8, half need to be carried over, but we have closed this path because this is freely supported and we have made it 0. There won't be any carryover. Similarly, from here also there will be no carryover. So from here also there will be no carryover. This should not be carried over, and here there is no carryover. So this. Then distributed end moment. For distributed end moment, we need to see every joint. So say joint A, we have 3.58. So minus 3.5 need to be applied, multiplied by this distribution factor is 0. Here 0 only, therefore there is no distributed end moment. So this indicates the procedure, that is the convergence of the moment distribution. Therefore, we can stop with this, and we need to add from this. So if you add from this minus 10.70, 2.580, we'll be getting this value. Similarly, add from this 7.85, 5. You should not use this value. That's why I told you to write using pencil. So now 7.85 plus 5.85 will be 13. Minus 16.8 plus 3.8 will be minus 30. And this is already 0. So we can have a check with the bending moment values. That is at fixed support will be having some moment. Mostly it will be negative bending moment. And at the continuous support, there should be balance of moments. So here balance of moments occurs. Therefore it is correct. And at the free support, there should be 0. So once you have the bending moment values, you can easily draw the once you have the final end moments, you can easily draw the bending moment diagram as well the shear force diagram. Thank you.